So we just talked about boiling point and how the normal boiling point is related to vapor pressure. So it's the boiling point is where the vapor pressure and the atmospheric pressure are equal to each other. We can relate our vapor pressure and our delta H of vaporization via this equation, which is the Clausius Claypeyron equation. And what that equation says is that the log of the vapor pressure versus the inverse of the absolute temperature is a linear function. So if we measure the vapor pressure and different temperatures, take the inverse of the temperature, the log of the pressure, we're going to get a straight line, and we can get the delta H of vaporization from that line. So here's the Clausius Claypeyron equation in linear form. So the natural log of the vapor pressure is equal to the opposite of the delta H of the vapor pressure over R. Notice this R is the gas constant, but it's in different units than we've used in the past. We use the units that have joules in them. So R in this case is equal to 8.314 joules per mole times Kelvin. So that times 1 over T plus the natural log of beta, and beta is specific to the liquid that you're looking at. So if you have a series of points, you can graph them and get a straight line. Or, if you get the straight line, then the slope of the line is, so the slope times your R value is your delta H of vaporization in joules per mole. Or we can use the 2-point form. So this is the 2-point form. So if you're given 2 pressures and 1 temperature, you can solve for the other temperature. Or if you're given 2 pressures and 2 temperatures, you can solve for a delta H of vaporization. So let's work through an example of that using the 2-point form. Propane has a normal boiling point of -42 degrees Celsius and a heat of vaporization of 19.04 kilojoules per mole. What is the vapor pressure of propane at 25 degrees Celsius? So this is the vapor pressure well above its boiling point. To do this, I like to write down what my P1, T1, P2, and T2 are, and then I know that my R value, which is going to come into play, is 8.314. So I can set my P1 to be my atmospheric pressure, 760 torr. And when my pressure is that, my temperature is -42 degrees Celsius, which if I add 273 to that, I get 231 Kelvin. My P2 is what I'm looking for. My T2 is 25 degrees Celsius, which is 298 K. So I know that my natural log of my P2, which is what I'm looking for, over 760 torr is equal to my negative delta H of vaporization, which I'm going to convert over to joules because my units on my R value is joules per mole K. So negative 19.04 times 10 to the third joules per mole divided by 8.314 joules per mole Kelvin times 1 over T2 is 298 minus 1 over T1 is 231. Then I can solve my left-hand side, so my natural log of P2 over 760 equals 2.22896. Then to get rid of my natural log, I'm going to take e to the power of both sides. So P2 over 760 is going to be 9.29, and so my P2 is equal to 7.060 times 10 to the third power torr.